Very good morning to all of you, and I hope everybody is doing well, everybody is enjoying the framework of quantum mechanics. And uh, in this video, my intuition is to basically uh, to compare the very two fundamental theories in quantum mechanics. One is the first quantization, and the other one is second quantization. And second quantization can also be taken as a basis of quantum field theory. Now, the point is that what we'll do is I'll be giving a comparison between the two theories. But before I make a formal kind of comparison between the two, rather it would be right for me if I start talking about the classical physics. And my point here is again to lay some state of stress on students that it's the curiosity that takes us from one level to another level, that moves us from one energy level to another energy level. It's the curiosity of the people who have worked in the field of science which has taken us to the present moment. So if I have to argue about it, and talking about the classical domain, the classical framework of particles. In classical framework, what we have point masses, and the position and the momenta of these point particles can exactly be measured. It can exactly be calculated. And talking about fields in the context of classical physics, we treat fields as some kind of continuous mediums. And the example is electromagnetic waves. The electromagnetic waves are purely treated as continuous media. Now, certainly, we are not able to understand things that are happening at the microscopic scale when we treat these particles as point masses. So certainly the questions would have arisen in the framework of science in the past, where people had curiosity about learning about the things that are actually happening at that level, at the microscopic level. Because the treatment of classical physics is a complete failure, talking about the systems at microscopic level. Say the problem of hydrogen atom, the problems of molecules, the problems that are connected with these microscopic particles. So certainly the people who have worked in this framework, they would have raised questions, and they would have come up with the curiosity, what if we treat these point masses as waves? And maybe this would have been the argument. Now, let's assume that these particles are not the point masses. Let's assume that these particles are waves, and replace replace the observables that we have in classical mechanics, the observables, and replace these observables with their corresponding operators. In classical domain, you can describe the system using these observables. You can calculate the observables, and the same calculations can be carried out in quantum domain, what we call as operators. We have position operator, we have momentum operator. Now the description is there. So it would have been some kind of curiosity in the man's mind that has led him to go with what if this microscopic particle is not a point mass. if I assume that this point particle is a wave, and if I assume that there is a corresponding operator for every observable in the classical world, and this has given the birth to what's called as first quantization, and the motion of the particles is described using Schrodinger's wave equation. Now again, there is a problem in this framework. The problem is that you can treat your systems, only those systems in which the number of the particles is conserved. You cannot use this formalism, the formalism of Schrodinger, where there is no conservation of number of the particles in your system which you are supposed to discuss, which you are supposed to learn. And another important problem is, come on, your first quantization is giving us the feasible results only in the non-relativistic zone. So there's a problem. There would have been a problem in that domain. There would have been a problem in that context. People would have raised questions. What if? What if? So this what if has certainly taken the scientific community from first quantization to the next quantization, what is called as second quantization, which is the basis of the quantum field theory. So the curiosity and the simple arguments would certainly have taken people to a more fundamental theory, a more naturalistic theory, a theory that could accommodate operators like creation operators and annihilation operators. And if we go back to the first quantization, we have the framework of these waves. We have the framework of these particles in the context of the Hilbert space. But Hilbert space cannot accommodate the additional particles. It cannot work for the particles which are destroyed in your system. So in second quantization, we start with an argument, what's called as Folk space. So in Folk space, you can precisely organize, you can precisely keep the number of the particles, even if the number of the particles in your system is not conserved. You can contain the things within the framework of the Folk space. So now there's again what if. So in the first quantization, what if particles are treated as waves? Now again, what if the particles are merely the excitations of some quantized field? Now your what if is taking you to the next level. It's taking you to the next more fundamental framework of understanding the nature of reality. So what if the wave function itself can be quantized? So if wave function can be quantized, why isn't it possible to quantize the field? Why isn't it possible to quantize the field? And when we work in this framework, what we can do is, assuming that your field can be quantized, assuming that your wave function can be quantized, we come up with the more fundamental realizations, with the more fundamental arguments, with the more fundamental nature of reality that's linked with these quantum particles. So now, what I'm trying to tell is that certainly it's the curiosity that has led these brilliant people to come to a level of the most general theory in quantum physics. So curiosity is always an important tool for anybody. This curiosity can be your part in science, it can be the part in your social science. Even this curiosity can be applied in any framework. So curiosity is a must. The questioning is a must. What if? So to give you a brief comparison between these two quantizations, let me start with this. So first quantization, it's basically the traditional framework of all that Bohr, Heisenberg, and Schrödinger. So you know all of these things of quantum mechanics. They're classical physics quantities like position and momentum. They are basically prompted to operators. The observables that we have, you take them to a domain of operators. And one of the key features of this first quantization is we have a wave function, psi of x. It describes the state of the single particle. And we have observables like momentum and energy. These observables, they basically become our operators. And Schrödinger equation is the basic equation that governs the dynamics of our system. And this first quantization is suitable for single or few particle systems. You can treat your particles, a single particle or a few particles in your system. And the example is the hydrogen atom, where the wave function evolves under the action of the potential of the nucleus. So this is the framework of, a compact framework of first quantization. Now talking about the second quantization, it is a more advanced formalism where fields and particles themselves are quantized. So as I said, you quantize the fields and you quantize the particles. And one of the key features of second quantization is your field operators act on a space, what's called as Fock space. And Fock space can accommodate your system in which you have variable number of particles, which is not the case, the case that can be handled in first quantization. So creation and annihilation operators, they automatically make their way in the Fock space, because you can add the particles to your system and you can remove the particles from your system. So this second quantization, it naturally handles systems with the variable number of particles, which is not the case with the first quantization. It's very suitable for quantum field theory. If you understand the second quantization at its root, then certainly it's a very basic building block of quantum field theory. So the examples, I have taken an example, electrons in a solid, where electron states are, you have electronic states, somewhere are created, somewhere these states are destroyed by the operators. So you can handle those problems in condensed matter using second quantization. To make a formal kind of comparison between the two, it will be right for me to read out the things exactly that are written here. So for first quantization, particles described by the wave function, as I said. In second quantization, particles are described by operators, and these operators are acting on these eigenstates. They're operating on these wave functions. Now talking about the mathematical framework, for first quantization, Schrödinger's equation, we have the basic equation, what's known as Schrödinger's equation, and we have Hilbert's space of wave function. And let me tell you here, this Hilbert space cannot accommodate, you cannot add and remove the particles from the Hilbert space in this framework. And in second quantization, where we have field theory, we have the Fock space of many particles. Here we have Fock space in second quantization, and in first quantization we have the Hilbert space. Now talking about the applicability, we first talked about the nature of the description, then we talked about the mathematical framework, then we talked about the applicability. Now this first quantization, we can utilize this first quantization on the systems, on the simple systems with fixed number of particles. You can neither add a particle to your system nor you can remove the particle from your system. And second quantization can be exercised on complex systems and the systems in which the number of particles is not constant. The number of particles are variable. So, talking about operators, in first quantization, what we have position and momentum as operators, as some basic examples. We have a position operator, we have a momentum operator. But in second quantization, we have creation and annihilation operators, what we call that a dagger and a. So, to conclude this brief introduction, because after this we'll try to learn how to quantize a Hamiltonian. That will be the basis. So, to conclude, first quantization provides the foundation of quantum mechanics, which is ideal for few particle systems. And second quantization extends this framework to handle many problems and quantum field phenomena effectively. And both frameworks are crucial. It's not that you will say you can think of one without another. In fact, we can see that the quantum field theory is more fundamental than that of the first quantization, which can merely be an approximation of second quantization. So both the frameworks are crucial, and with second quantization being more general, it's more general and more powerful for advanced physics problems. So, so now we are going to continue this lecture with how to quantize our Hamiltonian, which is composed of the non-interacting particles in terms of kinetic energy and then potential energy, and think of two-particle interaction, assuming that we have two particles and these two particles are interacting, and we will try to mathematically formulate this quantization of Hamiltonian. So, a very good morning to you, and today I'll be talking about, I'll just go with how to quantize Hamiltonian in the framework of second quantization. And I will start with my Hamiltonian, and the Hamiltonian, if I symbolize this Hamiltonian as H, I can think it as a combination of kinetic energy and plus potential energy, and your system might be in which you have interaction between the particles, right? So let me assume that my Hamiltonian is composed of that interaction term. And we know how to formulate these terms, how to formulate the kinetic energy, potential energy, and interaction energy in first quantization. And what would be the motivation of this video? The motivation is simply to write down the Hamiltonian in the framework of second quantization. So, if I choose my Hamiltonian H, and the kinetic energy part is non-interacting. That means the assumption is clear here that you don't have any interaction. You don't have any interaction between the particles, right? And I will start. So I had thought that maybe the camera is not connected to the phone. So now let's continue from here. So what we have been talking about is we want to quantize our Hamiltonian, okay, in the framework of second quantization. And what I was talking about was that when we talk about the kinetic energy term, we assume that the particles having kinetic energy, they don't interact with each other. So there is no interaction between the particles when you talk about the kinetic energy of the particles. The next term is the potential energy. The potential that we think in this framework is something like something that's happening from outside. This is not the potential that is existing within the framework which we are interested to discuss. It is the potential that is being utilized from outside to our system. And this potential is also an independent potential, right? And then we have the third term, which is interaction term, very complicated term. And even to frame, we can frame the interaction term, but then to actually exactly solve the interaction term, it takes numerous methods, it takes numerous hard work for the students to resolve the problem of interaction. Now, if I assume that this kinetic energy is T, okay, and the potential energy is V, right? And say this interaction energy is W. So this is my Hamiltonian, and I want to quantize my Hamiltonian. That's my target. That's my job. So I can think of kinetic energy. Now T is my kinetic energy. And if I have to write down this kinetic energy, assuming that there is no interaction between the particles, this kinetic energy can be written as sigma. Okay? Some Tj, where J runs from one to n number of particles. So this is my kinetic energy. This is my kinetic energy. And we can write down this kinetic energy in the framework of creation and annihilation operators. I believe that you have already done things in the framework of creation and annihilation operators, what we also call as ladder operators. So we can write down this kinetic energy as sigma. Before I proceed, let me cut it for the time being. So this is my kinetic energy. Okay. Now let's go with the potential. Now my potential is V, and I can write down this potential operator as sigma V J, and J goes on. Right? And then we have the interaction term, that's W. And this W can be written as sigma, say, G dash W G dash. Now, because this is the interaction term, you introduce a couple of indices. So you have three terms which you usually write in your first quantization. Now, what would I try to do is, I would like to write down kinetic energy and potential energy and the interaction energy in terms of second quantization, right? So, how do I write that? Come on. Now, if I have to write down this kinetic energy operator is sigma. I have to define a basis first, okay? So I will define a basis of, say, Ui. Okay, this is my basis. And if I have to write down this kinetic energy operator, this kinetic energy operator is sigma I and J. You have a number of non-interacting particles, and the matrix element of Ui, T, U, J, A, I, dagger, A, J. this is your expression for the kinetic energy operator. It's a quantized formulation of kinetic energy operator. And what this kinetic energy is, you can think of it as P cap by 2m as well. Right? Getting the point? Okay? So you can even include this momentum operator in the matrix element of ui and uj, and 1 by 2m can be outside the matrix. P square, yeah, sorry. It has to be P square, okay? It has to be P square. Okay, this is my kinetic energy, right? This is my kinetic energy. Now I want to write down the potential energy. Now here, you should keep this thing in mind. You have an equation for your kinetic energy operator, and you are writing it in quantized form, and you have the creation and annihilation operators. The equation is working in the same way as I told you before, right? Okay? So this is how you formulate. This is how you formulate the kinetic energy of all these particles which are not interacting with each other. So similarly, we can go for the potential energy. So for potential energy operator, what I will have? I will have sigma I and j, then sigma ui, then you will have v and uj, then you will have a dagger I, then you will have a annihilation j. Is this clear? So this is how you formulate the potential term, and assuming that this potential is, it's not an interactive potential. It's a potential without interactions. And then we have the third term. What is that? That is W. Right? Now this W is basically an interaction term. You are including the interaction between the electrons, say for the sake of argument. So how do we write this W? This W can be written as sigma I j k l. Then ui, uj, and then w, uk, and ijkl, ul. See your complicated matrix element. Okay? And then, how do you write down these creation and annihilation operators? A dagger I, then a dagger j, and then a k, and a l. Right? As I said to you before, this is the most complicated part of this Hamiltonian, and it certainly needs the rigorous work. Maybe in the framework of research, if you want to develop something new, this part of the Hamiltonian needs the rigorous work to be evaluated, right? So what happens to our Hamiltonian? So if I write my Hamiltonian now in quantized formulation, how will it look like? My Hamiltonian will look like sigma, this is ij, and then you have ui, ket of ui, then you have t, okay, let me write, and then uj, okay, then you have ai, dagger, then you have aj. This is my first term, plus the second term will be sigma ij, it will be ui, then v, and then uj, and then ai dagger, then aj. This is my second term. And the third term we will have is sigma ijkl. So here you have ui, uj, okay, it has to be the ket again, uj, and then you have v, and then, oh no, sorry, it has to be w, the interaction operator, and then you will have uk, and then you will have ul, and then you will have ai dagger, then aj dagger, then ak and al. Okay? Now this equation is looking so ugly, it looks so crazy. It's like some crazy thing is on the board, right? So let's try to boil down the first two parts. The first two parts, the kinetic energy part and the potential energy part. Try to boil down it and quantize it and see the beauty of that boiling down. And we will not touch this, the third part, let it be as it's for the time being. Right? So what should I do for that? For that, I would like to define a new basis. I would like to define a new basis. Say I have chosen ui. Okay, you give me any basis. U, V is existing as potential here. W is there. Yeah, alpha I think. Let's go with alpha. Okay. So what I have, I define a new basis, and that basis is alpha. Say I take alpha I. Right? Okay, if I think of this new basis, I will write down my Hamiltonian in this basis. How will that look like? That will look like H is equal to sigma ij. A new basis, alpha I, T plus V, alpha j. Then AI dagger AJ plus IJKL. And everything that is in the third part of our Hamiltonian, I will name that zeta. Don't want to make it because I'm not doing anything with it. Okay? So, now you see I have chosen a new basis, and it's quite evident that you can simply add the two quantities, the kinetic energy part and the potential energy part. Now I would go for this kinetic energy plus potential energy. It will lead us to a new operator, and let me call that operator as H naught, small h naught. H naught. Now if this operator acts on this operator acts on alpha I. What is this H naught? It's the combination of kinetic energy and potential energy. Right? Operator. Kinetic energy operator has momentum operator in it. And this momentum operator is a Hermitian operator. The potential operator is a Hermitian operator. Getting my point? So if you are dealing with a Hermitian operator, now this H naught is a Hermitian operator. So it is acting on your state. What you will expect from this? Quantized energy levels. So let me define that as EL. And you will come up with the same eigenstate. Because H naught is Hermitian. Because it's Hermitian operator. Right? So what will happen now? What we have H equal to sigma ij, then alpha I, then H naught plus alpha j, then A dagger I, then A j. And then you have the interaction term. I will call that interaction term as a whole as zeta. Clear? Okay. Now H naught, okay, I forgot the ket here. It has to be a cation. So what will this H naught alpha J give us? It will give us EL alpha J, isn't it? So H will be sigma ij, come on, and then sigma alpha I, then you will have EL, and then you will have alpha J, then you will have A dagger I, and then AJ plus zeta. Clear? Fine. Now what is EL? This is a constant because these are the quantized energy levels, right? So this EL will come out of my matrix. So what will H look like? So H will look like sigma ij EL, and then alpha I, alpha j. Then AI dagger AJ plus Z. I think nothing wrong with it. Okay? You see, we are boiling down our kinetic energy term, our potential energy term, to a situation where you have a quantized states of energy. You're quantizing it. You have quantized energy levels. Getting the point? So, EL is out. Now here we can think in terms of chronicle delta. So, this equation will exist only for I is equal to J. For all other values, it will vanish. For all other values, this bracket will vanish. It will show its existence only for I is equal to J. So what is H? H is sigma. Now I will write I. Okay? And then EL. And then AI gather. Then AJ. Then plus zeta. Now, what is the product of A dagger and A? Now, it is in terms of I and J. Yeah. It will give you a number operator. Number. You have boiled down everything into numbers. You multiply these numbers with EL, and you're framing, you're basically quantizing something that you want to quantize, right? So H, so here this AI dagger and AJ is the number operator. Just gives you the number. You multiply the number with the energy, so you are moving from one energy level to another energy level. So H will be sigma I EL N plus zeta. So you have seen how to quantize the non-interacting particles in our system, and you will see that we have boiled down that crazy framework of kinetic energy and potential energy into a discrete number formulation, and you add it with the interaction term. So I think here we'll stop, okay?